This is the first video for Chapter 8, Confidence Intervals, the Basics, Section 8.1. A large bank decided to study the call response times in its customer service department. The bank's goal was to have a representative answer an incoming call in less than 30 seconds. Figure 8.1 below is a histogram of the response times in a random sample of 241 calls to the bank's customer service center in a given month. What does the graph suggest about how well the bank is meeting its goal? Well, if you notice, 30 is right here, and we see that the vast majority of the calls are less than 30 seconds. So maybe you might interpret that the bank seems to be meeting its goal fairly well because the majority of calls are answered within 30 seconds. There are a few that are higher, and they're not much higher, 45 seconds, so it appears that the bank seems to be meeting its goal fairly well based on this sample of 241 calls. So the idea of this chapter here is illustrated by this graph because what we're going to be doing from now on in the course is we are going to say, hey, I've got a population out there that I'm trying to find out something about, and I don't know information about the population. So I'm going to take a sample and use that sample to help me decide something about the population, to help me estimate something, to help me make some sort of decision about the population based on a sample. Here's another example. The mystery mean activity. Let's say that we have a certain population with a given mean. Now what I've done on my calculator is I have stored a number and I've called it M, and I've hidden that number. And now I'm going to take and I'm assuming this number then is the mean of a normal distribution. So I'm now going to do random normal with mean of M, standard deviation of 20, and sample size of 16. So this is mu, this is sigma, and this is n, sample size. So I get then I take the mean of my sample. So in other words, this is an X bar. This is a sample mean. And I say, based on this sample mean, could I come up with a plausible interval of values that would be possible for the population mean? Now I gave this to different groups of students in the class and said, can you come up with a plan for calculating the sample mean, or calculating, estimating the population mean based on the sample? So most of them thought in terms of, okay, I've got an X bar. I know if the sample size is large enough, or if the original population is normal, which is what we're assuming here, that the distribution of sample means is approximately normal. So I've got this distribution of all these X bars, lots of X bars. And so I don't know what mu is. That's what I'm trying to figure out. So what's my best guess for the population mean? Well, what if I took the sample mean and I added a couple of standard deviations on either side to that? Would that be most likely the population mean would be in there somewhere? So we have to think about if we were to take X bar and add plus or minus the standard deviation. Now, is this the standard deviation of the population? No, it's the standard deviation of X bar. How much do the X bars vary from one another? So if we did sigma divided by the square root of n, maybe we could get kind of a general idea of the interval in which the true population mean would lie. So in this case, I would do 243.585 plus or minus 20 divided by the square root of 16. Well, 20 divided by the square root of 16 is 20 over 4, which is 5. So basically, I'm going to say that there's some interval, 248.6, if I added, I should actually make this the first one subtracting. So if I subtract 5, that would be 238.6, and if I added 5, that would be 248.6. So I'm saying this is my best guess for where the true population mean is. And it turns out that's a pretty good guess because it turns out that mu, or M in this case, is 245. So that's what I picked. So that's actually a very reasonable guess. We're so this is kind of just a thinking this through idea here, but we're going to be doing a more formal study of the sample mean in section 8.3. So how is this chapter different than chapter 7? In chapter 7, we were given facts about a population. We were given its center, its shape, its spread. So we knew the mean of the population, the proportion of in a population. And then we were asked what could happen in a sample from that population. And that's how we got our sampling distributions. That led to sampling distributions. So we would say, what does the distribution of sample means look like? What does the distribution of sample proportions look like? And we developed characteristics of those sampling distributions. But now in chapter 8 we are going to look more at the realistic application of statistics. That was the theoretical part. Now we say, what do we actually know? Well, we know information about a sample. And then based on that sample, we ask, what can we figure out about the population? So we're going, and this is known as inference, and this is what we're going to be doing the rest of the course, is inference. So let's start with a couple of definitions. The first definition is a point estimate. A point estimate is a single best guess, a single number, for the value of a population parameter, which is based on a statistic from a sample. So the point estimate for the population mean, mu, would be the sample mean. That would be my best guess for the population mean, and that would be x bar. So up here, what's my best guess for the population mean? Well, it was about 243, give or take some. I knew that it could vary, but that was my best guess. That was all I know. And then I based my interval on that. The point estimate for a population proportion, which is called p, would be the sample proportion, which of course is called p hat. And then this is one we haven't talked about as much, but the point estimate for the population standard deviation, sigma, is the sample standard deviation, which is symbolized with the letter S. Now, what's the problem with point estimates? Well, the point estimates are rarely correct. I'll scroll this down if you're still writing. They're rarely correct. They vary from the true population parameter. So we don't really know how correct we are. So that's the problem with point estimates. So we do something to help fix that problem. What we do to help fix that is we create an interval of probable values, just like we did in up here with our mystery mean example. So let's look at how that works. Let's say here that this is a distribution of sample means. And it has a particular standard or a particular population mean. It's centered around the population mean because I know that mu of x bar is equal to mu, the population mean. And I know that sigma of x bar is sigma divided by the square root of n. So that would be my mean and standard deviation. So this is a distribution of a bunch of x bars. Now, one thing I know about this is that 95% of all of the x bars, since this is a normal model, 95% of the x bars are within 2 standard deviations of the mean. I also know that x bar can vary, so x bar could be over here, it could be over here. We don't know where x bar can vary. It could be really close to me. It could even be way out here. X bar could even be way over in the tail here. So if I got any sample, the sample mean could vary, although the majority of the time, most of the sample means are going to be close to mu, within 2 standard deviations of the mean. So let me start by stating a couple things that might seem very obvious. First of all, the distance from mu to x bar, from x bar to mu is the same as the distance from mu to x bar. So I could say here, x bar is 1 standard deviation away from mu, but I could also say mu is 1 standard deviation away from x bar. Secondly, in 95% of the samples, x bar will be within 2 standard deviations of mu, which is what we just said. Therefore, in 95% of samples, mu will be within 2 standard deviations of x bar. That is the basis for what we're going to be doing with confidence intervals. So I've actually made a little movable distribution here that I can bring up. And I can say, if we center, if we look here, mu, or 95% of my x bars are within 2 standard deviations of mu. But I could also say, let's say x bar is here. If I make an interval that is 2 standard deviations away from x bar, I could say, look at that, 95% of the time there, mu is going to be within that interval. Okay, mu is going to be close, it's going to be within 2 standard deviations of x bar. So if x bar is moved all over the place, you know, most of the time mu is going to be within 2 standard deviations. But what if I got beyond 2 standard deviations from mu? Notice then I could have an x bar that ended up way in this tail, and then mu would not be in that interval within 2 standard deviations. But how often is that going to happen? Only about 5% of the time, because only about 5% of the time will x bar end up either here or here and be far enough away that that 2 standard deviation interval wouldn't capture the true mean. So this is the basis of a confidence interval. So starting with the next video, then we're going to look at some more definitions and details now about confidence intervals.